Okay, so the next aspect that we can now look at is what happens when we have sort of singularities in the structure. And what I want to talk about here is, this is again understanding how does a finite element program behave. It's sort of part of those, you can think of the basics. But what I want to show you here is essentially a model of a crack tip. So this is really this is now a model. What we have here is sort of this part here can roll, and I'm applying a uniform loading at the top. So I'm pulling this open. So you can think of it as half a model for a symmetric model of a crack tip. And this is sort of how we pull this crack tip open. And the question we're going to ask ourselves is first off, if we just look at this kind of loading, we expect to see a high stress concentration here. So that's really not just a stress concentration we see. There's a singularity there in a linealistic model. And so what I want to show you is that the stress here does not converge to finite value. As we make the mesh finer and finer and finer and finer, and I'm going to do it just within reason, so that we'll run on the laptops and stuff. But the point is, if we were to make this more fine and fine, this stress at that point will go to infinity. And it's not because something is wrong or broken. It's the nature of linealistic theory that at these sort of singularity points we can end up with infinite stresses. And so, obviously, from a real material, this thing would have been yielded, and that yielding zones would have sort of relaxed this. It's kept the stress finite. But we don't model the plasticity in this linealistic model, and so the stress will go to infinity. So we have to interpret these things also appropriately. We can't just then work with infinite stresses and as if it's now real. So this is an important point and a consideration to take. And so any sort of sharp corners that you would get that are essentially 90 degrees and smaller that you might find in models are lookout points for all possible singularities. And not all singularities are equally strong. You can have different strengths of them, so as the loading increases, they will go to infinity at different rates. So that's important just to get taken note. So what I want to show you is essentially just, this is now the 100 times magnified deformed structure. So let's maybe just run it first without the 100 magnification, and the crack Q810 file. What I want to just show you is, let's open that file quickly, crack Q810 files. Oh, that is not, that doesn't look right. What is that file we were talking about now? Crack Q810. Crack Q810. So I open the output file. So what we see essentially is the node. There's node numbers there. I just want to show you what example node numbers we have. So we only have 341. Again, we can see here now what kind of units we are plotting here. So this maybe looks like something that might be more representative of something in meters. It goes up to about 0.8 meters. There's element type, plane stress. It's elements, Q8 elements again. Again, this first was the outside nodes of the element. This is the mid-side nodes of the element. Modal positions. There's the Young's modulus here, 210. Oh, so if you look at this, this is 210. So this is more like 210 gigapascal now. So thickness 1. So this is then a millimeter kind of scenario. So this, if we think of this as millimeters, oh, so you see here it goes up to 1 as well. You didn't realize that. So think of this as 1 millimeter, this maximum distance there, this model, and goes to up about 0.8 millimeters. So this is quite a small model, 0.8 and 1 millimeter sample that we have. Okay, so it's a really small part of the material. But this is just indicating to me that the implication is that, that this is sort of more representative of what do I want to say now? I've lost my thought. Small sample that we have. Okay, then 210 gigapascal sample there. Okay, so 210,000 MPa. Good. We look at the boundary nodes. If I look at this, this suggests that we're operating a boundary in the y direction. We're applying this prescribed displacements. So we are putting 0.0 0.02 millimeter prescribed displacement. So this is boundary. So this is prescribed not loading. The C load is essentially the loading again, zero traction, just to make sure the program doesn't crash. Okay, so let's go and see what this boils down to. If you run this 1 millimeter, so you can see now, you won't see lots happening. My magic is not. So if I go back to this 1 millimeter, so we can see the deformed, undeformed, you can't see squat happening, there's really very little happening. You can see essentially a von Mises stress. Look at that. So this loading that we've applied, a really small prescribed displacement that we've applied already, has resulted now in a von Mises stress at this crack tip here of 2175 MPa. Okay, so already a 2 gigapascal stress there. Isochromatic, look at this beautiful isochromatic that you get out. It's quite a coarse mesh. Remember, this is only 341 elements, but you can see again discontinuities. It's not, everything is not nice and smooth. Yeah, you can see sort of interstress discontinuities there. You can see some jiggery stuff. But if you look at this sigma XX 1 gigapascal. Isochromatics, if you look at this 1.7 gigapascal for sigma YY at the tip there, look at and then essentially the shears, we are at 0.17 gigapascal. Okay, so these are stresses that are for any material would have yielded long gone. Okay, but let's go and see to what happens now. If let's just make it run again, magnification factor of 100, you can just beautifully see again, just a reminder of what you see. This is the opening of the crack tip. This is now with the magnification of 5, and the rest of the stuff will stay the same as magnified. What we can do now is say, let's take this same model and make look at if you use more elements. So crack Q820. I'm going to open that file now, crack Q820. And previously, that's a reminder, crack Q810, we essentially had a total of 100 elements. Okay, so that was the number of elements that we had and a number of 341 nodes. But let's look at the number of elements, 100 elements. I'm going now to the _20 file, and when I look at that, I see I'm going up to the number of nodes is already considerably more, 1241, and if I go towards the number of elements, I'm going to 400. Okay, so we're going from 100 elements to 400 elements, and all the rest stays the same. Okay, so all the rest is the same. And so we have some zero prescribed displacements, and we essentially have so what you see is, again, all of them are in the y direction. I've got to mention in the previous file, so they can move an x at the bottom here. They can roll here, but they can't move in y. Okay, so if you run this again with a magnification factor of 100, what we see now is how the stress is going to vary. So what I just remind you is, let's look at the von Mises stress. Von Mises is 2175 at that crack tip. Okay, all I'm doing now, I'm doing exactly the same loading. Only difference is we are essentially using more elements to model this. Now we stress von Mises going from 2100 to 2900. You see that? Look at the sigma XX 1500, sigma YY 2400, shear 168. Okay, so that is essentially that. So let's look at sigma YY 24, and it was in the previous time we modeled it with the only the 10 element, it's the _10, 1798. Now it's going up to 2433. Now if I use 50, so I'm going from 20 to 50. Let's open up that file, _50, and I'm not going to run the _100, and I'm actually not including it. It's just, it will break. So the number of nodes we can see is 2601. So that's what we see there. Number of elements 2500. Okay, so that's really what we have with the number of elements we're running here. Oh, this is the old input file, it seems. Oh, this one. Oh, this is the Q4. Sorry, I opened the wrong file here. Ooh, Q8 _50. My apologies. That's also the old input file. Okay, I wanted to say that's not the star one. Okay, so forget that previous input file. That's the old format. So now we have 7,700 nodes, elements, going from 400 to 2,500. You can still see everything is the same kind of loading that we have. All the rest stays the same. Okay. So let's see what happens if I run this one. And magic, working again. So let's look at what's going on here. Now the stress, so look at that beautiful information that we see there. The stress there has now gone up to 5,400 from 2,000 for the von Mises, from 2,700 if I recall, 2,900 has now gone up to 5,400. And as a matter of fact, as I make this mesh finer and finer, it will keep on increasing. You can see that stress, just with the corrected there. Look at this beautiful isochromatic. Look at that high stress concentration there. Unload it. Look at these fringes and look at this enormous amount of fringes as they increase here. Extreme stress concentration. Look at that sigma XX, but look at this beautiful pattern of stresses that you see there, and that corresponds very well to the analytical solutions as well. There's analytical models that have been derived for stress, distribution of stress concentration at the crack tips. Look at this shear that you see here, which is essentially, it will be closely related to what you would see in yielding and plasticity, because plasticity is a shear-driven event. So what drives plastic deformation in metals is really just shear. So what you would see is essentially maximum shear. If we were to go and compute that and look at that, that would correspond quite well. This is sort of reminiscent of what you would expect to see maybe from a plastic-driven kind of deformation. Okay, so look, we're not going to talk too much about plasticity, but essentially maximum shear stress is what drives plastic deformation. But beautiful if you look at that. Those patterns, I think they're quite nice, but it's extreme kind of stress that you see there. So this is now gone up to 421, almost half a gigapascal for this shear in the XY coordinate system. Okay, hopefully this gives you a good idea of where we're going. Validation and seeing some more complex things, complex structures, so that you feel like we are at least, what we've learned here is at least applicable for engineering in the 2020s. But this is really just to make sure that you understand, going through this process of really simplifying the problem, understanding that well, and then just upscaling the number of elements. This is really all that we've done. We've just used lots of elements now. We are really able to get full complexity kind of descriptions of what's going on.